Thank you all for coming. I'm Madeleine Waller, and as I'll be presenting our paper, my colleague Odinaldo Rodrigues, who's at the front here, Beyond Consistency, Nuanced Metrics for Individual Fairness. And what kind of system are we talking about in this context? Well, I'm looking specifically at algorithmic decision-making systems based on binary classifications, so ones that give positive or negative classifications for an individual that leads to some kind of real-world positive or negative decision. And typically these might be based on some machine learning model, perhaps black box, and we've been looking at the context of structured tabular data storing information about those individuals. Thanks to the previous talk for introducing group fairness. I'm not focusing on that, I'm going to be looking at individual fairness, so a bit different, and specifically the notion of consistency. So looking at ensuring similar individuals are treated the same. And this is further motivated by text in the UK Equality Act, for example, and other EU non-discrimination laws, this idea of prima facie discrimination, which essentially states that an individual can show that they've been discriminated against by showing that there are similar individuals to them that have been treated differently or been given a different decision. So this is the kind of notion we've been looking into. And this has been defined in the algorithmic fairness literature before. So this is Zemel et al. 2013, Learning Fair Representations, defined this consistency score, which essentially measures the overall level of disparity in the data sets, in the classifications of individuals with respect to those most similar individuals. So it provides an average over all of the individuals about how differently they are treated to their similar individuals. And we'll come on to this a bit more in a minute, but I've mentioned similar individuals a lot of times now, but what do we actually mean by that? Obviously, this is incredibly contextual and domain dependent, and there's another line of work that kind of works on defining similarity within different types of data. For our structured tabular data, we kind of need to think about how to actually firstly categorize each attribute we have, how to calculate the distance between values of those attributes. So are they categorical attributes, and therefore the distance is 0 if they're the same and 1 if they're different, for example, or are there numerical attributes that we need to take some numerical range over, and then how to calculate the overall distance, so how do we aggregate these individual distances using Manhattan distance, for example, and then finally, how do we actually select those similar individuals given those distances? So do we take a k nearest neighbors approach, for example, and take the 5 most similar individuals, or do we have a distance threshold, for example, and say, well, actually, if you're within that distance threshold, then you're considered similar. So a lot of the work we've been doing is exploring this consistency score. It's implemented in IBM's AI Fairness Toolkit, for example, and mentioned a lot throughout the literature, but there's actually very few works that actually explore it or use it in any sense in their experiments. So we focus on exploring it, specifically on the adult census, Compass and German credit datasets, widely available datasets. We define 4 definitions of similarity for our experiments based on some of the criteria I previously went through. And essentially we found that changing this definition of similarity does not greatly impact the consistency score. So the consistency score remained relatively stable even when we were defining similarity in very different ways. So we kind of hypothesized on this, that actually maybe this consistency score does not capture what we want it to capture, does not sufficiently capture the fairness at that individual level, or consider how those specific individuals might actually be impacted. By the nature of the metric, it's still an average over all of the individuals, so maybe there's some individuals that we're not really accounting for, or they're being hidden by this score. So we wanted to dig in further, so we proposed this zoom in of the consistency score, this individual consistency, which is the proportion of a selected individual's most similar individual with the same classification. So in this case, you can see there's 3 of the 5 similar individuals that have been selected have the same classification as the selected individual. Therefore, we have an individual consistency score of 3 out of 5, 0.6. And based on this, we wanted to propose some potential new metrics to be able to explore actually, is the consistency score representing what we want it to represent, or is there other ways that we can kind of explore the individual fairness of our data sets? Because we understand that this is very useful from a specific individual perspective, but stakeholders and people engaging with the system still like to see aggregate metrics over all the data sets and all the classifications. So first we define this similarity robustness of individual consistency score. I'm going to go through these metrics quite quickly, but obviously all the details are in the paper and all the notation, and I'm happy to answer any questions. So this essentially quantifies the proportion of individuals for which the individual consistency changes across a threshold when changing the definition of similarity. So for example, you could set the threshold to 0.5, meaning that this score would quantify how many individuals go from having an individual consistency below 0.5 to above 0.5, or vice versa. So significantly changing the perceived individual fairness for that individual. And that is exactly what we found using this metric, is that is the case. A significant proportion of individuals go from being treated the same to being treated differently, or vice versa to their similar individuals, which the consistency score itself did not capture, because even though consistency score remained stable, relative to the same value, because it was averaging over these values, actual individuals in the data set were being treated significantly differently. Another metric we propose is this low individual consistency count, which is simply the count of individuals in the data set for which that individual consistency is below some threshold. So this essentially gives us a count of the individuals that we're particularly concerned about. So again, you could set this threshold to 0.5, thinking about which individuals are treated significantly differently from their similar individuals, and this gives us an idea of the scale of impact as well. So not just finding a proportion, we can see actually maybe 10 individuals impacted is less important to us than hundreds of thousands, even if the proportion is the same. But similarly, we also provide the proportional consistency score, which is the proportion of individuals for which the individual consistency is above some threshold, so mirrors this consistency score, but now if the individual consistency is below the threshold that you've selected, it counts it as 0 in this proportional weighting. So we don't count it in our thing. So this measures how many are consistent with the similar individuals according to the threshold. Another metric, balance, condition, consistency, is similar, but instead of just taking the proportion of how many individuals are differently impacted, we now average over the actual individual consistency above some threshold. So this gives even greater weight to those ones that are treated significantly differently. So when we're averaging over the consistency, if it's below the threshold, then we count it as 0 in the overall average. And even further, you can weight we can penalize even further for those ones that are treated significantly differently. So if you're below the threshold, we can also set a penalty. Perhaps, well, we've done -1 in our experiments to give greater weight in the overall calculation to those individuals that are treated, who have an individual consistency below that threshold. And we did do a lot of experiments results. This is, just an overview of all of the metrics, and we tried to make it clearer in the paper and what kind of scenarios you would try and use these. And essentially, we found that actually altering the definition of similar individuals can significantly affect this proportion with a differing classification, and that our new aggregate metrics give greater consideration to those individuals that are treated significantly differently. And we believe our metrics, provide this more nuanced understanding of how individual fairness for binary reclassification, and a good overview of it. Obviously, there's some future work here that we need to think about, and that is similarity is, very contextual, not easily generalizable. So we really need to think about how to make sure we pick and experiment with the right similarity definitions and what they mean. This is, as I said, a strand of work already. But also, we only currently define similarity for tabular data. It'd be interesting to see if we could do it with text or images and how that might extend. In theory, if you had the similarity definition, you could be able to use our metrics. Currently, they're only used for detection, not mitigation, so it'd be interesting to see if we can involve any of these in the loss function, for example, in the model, to see if we can improve the individual fairness. And also a bit more work on helping stakeholders understand and use the metrics through different toolkits and frameworks. We're currently starting to work on that now through the development of a Python package already, which is very early development, which has a dashboard which enables you to play around with all these metrics and dig into the different individuals and their individual consistencies. And thank you very much for listening, and happy to take any questions.